discussions. Vibration isolations. Let me see. Let me go to Q factors first, because this one, there's one question in the homework. So let me cover this topic, and then we go back to go the vibration isolation. Because today I like to finish the lectures by 12:30 and go for the important meeting. So I try to finish this topic first. Okay. So the first one, let's define what is a Q factors. So basically, in general, we consider these response. So if you remember our magnification factors, okay, so this one is we defined as the magnification factor. Okay, so this is R. And R, by definition, that is the frequency ratios between the working frequency and natural frequencies. And this is 1. So if you remember, we have R for certain, say, damping ratio equal to certain numbers. Okay? And we have a different damping ratio, then we have a different curve like this. Okay? And last time we have learned the formula is corresponding to which value of the R, and then we have a maximum value here. Okay? So basically for this curve, it's very easy. Simply two major features we want to find out. The first one is what is the maximum value of the peak. Okay, what's the magnitude of the peak? And then when the peak happens, so that is corresponding to R star. And that one, again, we went over last time. For quality, for Q factors, simply is this. We simply look at any single curve. So let me show this one again. So this is R, and this is the X over delta ST. We simply look at one curve. Okay? We simply look at any curve and associate it with certain damping ratio. The damping ratio, if that is small enough, we should expect certain peak. And on the other side, if the damping ratio is big enough, then that is monotonically decreasing. We won't see any peak. Okay. So if you want expecting a system with showing the peak like this one, then you must have the system have a small damping. Okay. And we keep this in mind. Then we further look into the definition of the Q factors. So basically, it's pretty easy. The Q factors simply is another name or another definition of the maximums of the magnification factors. So basically, if you like, you can say, basically Q factors is the magnitude of the peak. That's it. That's it, simple. If you look at this definition, that is the maximum of the magnification factors. Basically, is saying this value defined as the Q factors. Okay, so basically they're using the different name, and I believe the Q factors are was originally defined or come up with from the people working in the power related, for example, electrical engineering. Okay, they using this one, they look at the system from the different comprehensions, and so they come up with this one. And the Q factors, again, basically Q factors equivalent to the peak, magnitude of the peak. Keep this in mind. And then we, starting from here, so you can see the magnification factors is described by these equations. This equation described by the curve, okay? And that can be calculated any family, any curve in this family can be described like that by this equation, and that equation will be seen before. Depends on the different value of the zeta, and then we have the p. And so in particular here, if you see, if we plug in r equal to 1, okay, so if we plug in r equal to 1, then the magnitude of this ratio, these magnification factors become this value. if you plug in r equal to 1, the first term disappears. And then here the second term becomes 2 zeta squared. And after square root, we simply become this one. So to be concise, the Q factors are the numbers or the magnitude of this curve corresponding at r equal to 1. Good? Yes?
So, but the maximum is not always at r equal to 1?
Not always.
Okay,
yeah,
so
not always. So a little bit offset a little bit.
Okay.
But for convenience, the people simply say, well, I just take the added resonance and I measure the magnitude. I define that magnitude as the Q factors. But you know, everyone right now, we know that the maximum actually not occurred at here a little bit off, right? So basically the Q factors say, well, that is the maximum, really is not maximum. But that's another definition. So I would say that pretty much close. If you want to do the very quick approximation, this Q factor will be good enough. But if you are picky, like Travis, then you go for the detailed calculations. Okay? Okay, so basically the Q factors is the quantity to measure the value here, and the corresponding is the added resonance. Another viewpoint, I put the notes here. Another viewpoint of the Q factors, this is not important, is this. Assuming if we have a system that have a very small damping ratio, for example, in particular, we define how small is small, then we say the damping ratio less than 0.05, we say that damping ratio is small. Okay, so for small damping ratio, then we can approximate. We remember from our maximum value, Travis, that equation is here. Okay, so that is the maximum here. If we plug in and then assuming the damping ratio is almost 0, so basically this term can be approximated by 1. We simply drop the approximate damping ratio equal to 1. So in this way, the maximum value is approximated by this number. So this note provides us the approximated viewpoint of the maximum. Okay, but anyhow, that one, leaving this for you to take it. I think that take this one. This is the formal definitions. So with this one in mind, and here I want to talk about the system dynamics. The system dynamics in terms of the spectrum view. Okay, spectrum. That means we'll look at system dynamics in terms of the frequency response, and we call the spectrum response. So keep this in mind, and let me get rid of this one. So right now we focus on the Q factors. That is our Q factors. So most often we look at the systems from the spectrum viewpoint. Again, we say the spectrum. That means in terms of the frequency behavior. If we give the system excitation at certain frequencies, the system will respond. And in terms of, say, at this R here, we have this magnitude. At different R value, we have a different magnification factors, which means different X value. Okay. Looking at the systems from the spectrum's viewpoint, which means from the frequency viewpoint, in my viewpoint, in my personal feeling, is not very common for mechanical systems. In particular, here I say the mechanical system is kind of bulky. We have mass, and those mass pretty much sometimes is kind of bulky, big one. So for bulky traditional mechanical systems, its natural frequencies or its system response is slow. The slow, that means simply just like elephant. If you give elephant excitation, it moves, but time constant, which means the response time is a little bit slower. Compared to electronic system. Electronic systems in terms of R, L, C, and you can design the system time constant or system response that's basically in, well, they measure in kHz, in 1000 Hertz or in megahertz. Okay, so in terms of that one, then the system response can be more reasonably discussed in terms of frequency domain here, because not really. The system response at the different frequencies, and really we can see something in the reasonable range of the time. Okay, so here I would say this one is more common in electrical engineering viewpoint rather than the mechanical. But here our textbook address this one. We go forward, and there's two quantities we want to go over here, and we can look at the slides. The first quantity we want to define is the bandwidth. The bandwidth simply is the range of the frequency. In this graph is this one, this distance in terms of in the unit of the frequencies. So this one is called the bandwidth. Okay, for example, say right now this has a unit, say in terms of hertz. So if say we have R1 say 1 hertz, R2 say 10 hertz, then the bandwidth is 9 hertz. No, I shouldn't say that one. Sorry, the bandwidth is denoting is between 1 and 10. So the bandwidth is to denote the range in the frequencies. Okay, and we said the systems have the bandwidth between 1 and 10 hertz. That means the system will be very excited, will be the most exciting if you give the frequency in this range. Okay, and so exactly how can we define the boundaries of the bandwidth is by doing this. Again, the first one, you are given the system damping ratio, zeta. So you simply calculate 1/2 zeta, and that is the Q factors. And basically that is approximation of the peak here, okay? With that number ready, then you simply divide that numbers by square of 2. And once you have this number, and then you simply make that line and intersect 2 points. And corresponding to 2 points, that is the R value, frequency value, then we define that is the boundaries of the bandwidth. Easy. Okay. So that's the definitions. So in this way, again, to get the bandwidth, you simply need to calculate these numbers, okay? And then once you have that number, you simply make the intersections with this the curve, and then you get this one. The question is why we have to divide by square 2? Can we divide by any other numbers? Yes, you could. If you are the pioneer in this field, then whatever you define reasonably, people just follow you. Okay. And in the very beginning, very early, why the people decide to divide by square of 2? Because they pick is this. They thinking, I just want to pick up any reference or any threshold. When the system's response drop to, they call the half power point. The half power point is such that compared to the peak, then compared to the certain frequency operating at the peak, if that system response can be dropped off compared to in terms of the power, that means energy per second. So basically, if the system's response drop compared to its peak performance dropped by half of the energy, then we call the half power point. Okay, so again, this axis denote is the magnitude magnifications, and so x representing is certain kind of the magnitude or displacement related term. In terms of the power or energy, that basically is saying the power or energy is proportional to x squared. So if we want to go to the half power point, that means we go to the x square root of the x, and then that means corresponding here is the energy. So say if this is the energy, and energy is proportional to x squared, displacement square, right? That is the kx squared, that is the strain energy, right? So this is a half power, so if we drop is 0.5 of the half power equivalent to this one, that means is equivalent to is equivalent energy. That means equivalent to the half power of the energy, that means the x squared divided by 2. Okay, so that means once we transform into here, that equivalent is at this point here. Okay, so that reason, if you want to determine the half power point, you divide by 0.2. The square of 2. So once we have this one, then you can simply, from the curve, we simply drop it, and then we can determine graphically we can easily approximate the boundaries. And on the other side, if you want to calculate precisely, and here I'm going to show you the detailed calculations. Before doing that, here is the examples of the bandwidth. So for example, for certain systems, we have such like this. So this one has the pretty much flat in the lower frequency range. And basically here, all the points maintaining is above the half power point. So in this way, once we determine using the graphical approach to find the intersections, we can only find the upper limit here. So that means intersecting here. So that means the bandwidth of the system is from omega from this point and then downward, including all the lower frequency. In other certain frequencies, something like this one, this is maybe the appropriate, maybe the small damping ratio that we do. Using the half power point we are able to find the 2 points at the intersections, then the bandwidths are defined within this range. Okay, so that's a kind of the quick example here. And in this slide, I summarize, and in theory, the theoretical expressions, how to determine the boundaries of the bandwidth theoretically. And this is a very good approximation. So that means if you would know the damping ratio, you simply plug in the two results, and you can get finding the range of the bandwidth. And how to do it? So here I give you the calculations to show why is that. Okay, so again from here, the boundaries of the bandwidth R1, which is omega 1 divided by omega n, and R2, omega 2 divided by omega n. So that means at a particular working frequency, omega 1 and omega 2, that will correspond to R1, R2 here. So are determined by this. We know that the R1, R2 are the corresponding R value, and let's write out the curve. So the magnification curve has this equation here. Again, we describe this curve, this is called the magnification factors, and that curve is given exactly by this equation, 1 minus R squared plus 2 zeta R squared. Okay, so that is the equation for the curve. And we want to get the R value here. So basically here, that is we're setting the value of the curve equal to how much? Equal to the half point value here, right? So that is equal to Q over square 2. And what is Q? Q, by our definition, that Q value is the value of this R curve and the resonance. So if you remember that previous equation, that is 2 zeta. Right, the Q value equal to 1 over 2 zeta. So we simply plug into here and then to solve for unknown, to solve for R. And the root will be equal to R1 and R2. In theoretical calculation, we can do this. So simply from here you can see that is the R will be the function of zeta. And here is the certain nonlinear polynomial, and then we try to solve for it. And how to do that one, maybe if you like, you can take the square on the both sides to first eliminate this kind of bothersome square root, and we try that one first. Okay, so take square on both sides. So that will be equal to let me do the result here. So that will be 148 zeta squared equal to 1 minus R squared plus 2 zeta R squared. Okay. So if we take the square root on this one, then we rearrange, and that will become r to the fourth minus r squared 2 minus 4 zeta squared plus 1 minus a zeta squared equal to 0. So from here, if you take this one, say you can solve for r squared would be equal to, using this equation, x plus ax plus b equal to 0, then we know the root is minus abc, and 2a minus b plus b squared minus 4ac, right? So we're simply using this formula applied to here. So the r value we plug in here carefully, and that will be 2a and minus b, 2 minus 4 zeta squared plus minus b squared minus 4ac, so 2 minus 4 zeta squared minus 4ac, 4 times a times c. Okay, as we simply implement it, you don't need to write this one. So basically r will have the roots will be equal to and 1 minus 2 zeta and 1 plus 2 zeta. And here we do the approximate, basically we ignore the higher order terms, because zeta here is small. So zeta square or whatever the force, we drop it. So eventually we will have the 2 terms here. Okay. So this is a smaller value, this is a larger value. So smaller value go to R1 and larger value go to R2. Good? Okay. So now we solve for this one, and that is the first properties. R1, R2 will be equal to this one. These are the first properties. And then another one that people come up with a very good approximation is this. For small damping ratio, we know the definitions of the Q factors is equal to 1 over 2 zeta. Again, if you take the difference between the bandwidth here, if you take the algebraic the difference between R2 and say take R2 minus R1, and you take the inverse of that value, then you can find approximation. Basically, the Q factor is approximately equal to this. Again, this equation is good enough for small damping. If you prefer not to take this approximation, you simply just go to original. I think using 1 divided by 2 zeta, that is very simple enough. But on the other side, many times, in particular in electrical engineering, most of the time they're dealing with is a bandwidth. If you have any project work with them about electronic circuit design, their always first concern is the bandwidth, because they want to know from the bandwidth, they would know, first one, how quick the system response will be. The second one, the bandwidth will help us to do certain as a filter. Okay, sometimes the circuit can be the filter to only selectively working with good signals and then eliminate some undesired. Okay, so sometimes they want to get a feeling about the bandwidth in the way in the filters, or they want to be amplifications. Okay, so from here, if they want to use the curve as the filters, as a filter, that means to eliminate the noise signal. So if they would know the noise signal, say in this range, they simply design their curve to avoid that kind of range. On the other side, if they want to do the magnifications, say the power amplifier or the amplification, they simply put this range, the bandwidth, to overlap the frequencies they want to design. Overlap there, they will guarantee they will get amplified signal as well. So always the bandwidth is right away is to tell the kind of characteristic, the kind of fingerprint of the systems. Okay, so that is the information, and so here is a little bit more introductions, kind of try to get some taste of about the system dynamics viewpoint of this kind of curve, and here is more qualitative. again, the purpose of this one is to reinforce your feeling, not to give you the knowledge, but get the feelings about the systems. Okay. So to reduce the vibrations, that means you don't want the X value. The X is the magnifications, right? So if you remember in our steady state, the steady state response is X, for example, cosine omega t minus b, something like this one. And this is the amplitude. If we want to eliminate or reduce the system's vibrations, we wish the X value can be small as possible. To have the small values of X, so basically here we're falling into our desired range of the operations in terms of omega, in terms of the value of the omega, our frequency, working frequency. You better select your working frequency in which range, either in this range or in this range. That means if you want to have the reductions in vibration level, so that means you better to choose your working frequency outside the bandwidth. Got it? Graphically, you know that if this range or this range can give you a good result. Okay. On the other side, if we wish to enhance the system's sensitivity in responding to certain signal or certain excitation, that means response to certain external loading. If we want to increase the sensitivity, then system response must be big enough to pick that signal. If the signal is enough for engineer to easily identify, okay, or the signal is strong enough to have a better resolutions. In this way, then you better to design your system operation range inside within the bandwidth range. So that's the different concept, just like I said before a few minutes ago about this one. Okay. So here is the different viewpoint of these things, and then here you can see I highlight this light won't be able, but here I use a yellow to highlight the bandwidth regions. This is a very interesting topic. Let me explain a little bit. So basically the Q factors in terms of exercise is very straightforward, and you simply need to know is how to determine the Q factors. The Q factor simply is 1 over density ratio, and then you simply need to know how to determine the bandwidth, and that is R1, R2, and find the two values. The calculation is pretty straightforward, but a lot of the applications. So here I'm showing is we look at the mechanical systems first. Okay, so basically this system has the, let me explain. We look at this one, the 3D viewpoint. Basically here is kind of the empty space has been etched, has been moved away from the, we call the substrate, the supporting base. And in between, basically this is the kind of the double clamped beam, okay, and that's an elastic beam. Elastic beam, basically they have the material properties like E, I, and the length L. So from E, I, and length L, we know that we can always be able to calculate equivalent spring constant. So this beam, you can see that is basically a certain spring. And this beam also has a mass. So basically with the spring with mass, we know this one has certain natural frequencies. Certain natural frequencies to behave. Okay. And the purpose of this design is the scale of such a design is in very small. Usually we are measuring in micron. The micron, that means 100 micron basically is about the diameter of the human's hair. Just kind of give you a feeling. 100 micron, the human, if you put them one, and then who want to sacrifice, I can, you know. Even if I demonstrate here, you won't be. But here, in general average, the human hair's diameter is about 100 micron. 100 micron basically is a 0.1 millimeter, and that barely is our eyes we can really see, and that has been approaching to our kind of resolution, our eyesight resolution pretty much. But for young people like you can maybe see even thinner. Okay, but for me, no. Usually the scale we measure is in terms of at the unit of the micron. The way this one has been using they call the semiconductor technologies to do this kind of the manufacturing, and they're using depositions and etching of the based upon the silicon substrate. Silicon substrate basically just like pure sand or glass, and they can etch, which means remove the certain material away because that is a pure crystal, and doing right can be easily knock out certain portion of the material with very sharp sight. Okay, so they do this one, and then on which they can continuously, they call the flow steps or flow step by step. They can deposit on the substrate with certain materials like metal, like other polymer, for example, and then they can repeat the etching deposition process to achieve the desired the pattern the generations. Eventually, they can come up with this kind of the beam, and the beam have the certain metal layer for and not only for mechanical function but also for electrical functions, like the signal transferring or the power transferring, something like this one. This one for this particular design has been I pick up is they using this one as a part of the communications, and say your cell phone. Usually cell phone we talk about is in terms of the gigahertz kind of the frequency for something. Okay, so for communications, they do need some kind of the components they can work with the frequency and the gigahertz range. Okay, so that means that kind of define the working range is in that kind of high. So that means the system's natural frequencies must be very, very high to work in that way. And to have the high natural frequencies, the only way, I think the quickest way to do it is to shrink the system's dimensions. If you have a very small m, and then equivalent you have a large k, then easily natural frequencies can be very high. Right now, the only easiest way to do it is go to such we call the micro or nano fabrications and semiconductors, the photolithography kind of the techniques. Okay, but anyhow, so right now this is the kind of the structural, the mechanical structures like this, and right now we know that this beam is working as the something to provide some kind of frequency information for something. Okay, so keep those in mind. And this is equivalent the circuit, and that is not our class concern. We can drop it. So keep these things, and then they're going to have the design. Say this is aluminum nitride. It's some kind of the alloy, and to working as the insulation, the supporting layer, and then just like this one. So from here, I think the platinum is working as the electropad, the source and drain or whatever. Okay. So now we design, and in the way we want to see the comparison. So for this example, we compare the device Q factors. Okay, really that they're picking up this concept and with certain conditions. So here is the Q curve, magnification factors curve. Okay, that exactly is what we learned. But because this system is continuous system, that means they have the multiple degrees of freedom, equivalent to say they have more than one mass block, 2, 3, infinite number of the mass blocks. In this way, we will see the not only major peak, but also minor peak something, because there's a multiple degree freedoms. Okay, so not surprised, we expecting in real case like this. So for example, say for this case in the fabrication process, in particular, the people they try to change the aluminum nitride, like the level, the layer. So they're using the 300 micron thick of the beam, and here they compare with the 200 micron the thick beam. So basically, they're working on the different. I forgot is a width or depth. I forgot, but basically they change the dimensions. They can see corresponding the systems, the Q value, the curve different, kind of shifting at to the different range. So this is a very practical example to show that the Q factor really has been commonly used in the industry and for something. Okay. And again, because that system is so small, so pay attention to this one. Usually for traditional mechanical systems, you won't see such high frequencies. If say go to the machine shop, we have a very good CNC machine. And that one, if you'll be able to measure his dynamics, the characteristics, and won't be that big. Okay, so if you would drive the machine to that kind of big frequencies, Eric will give away. Okay, so I think that is pretty much is the way. And